Today, we're diving into a huge idea from the one and only Richard Feynman. Think of it like a detective story, a journey that reveals why trying to simulate our universe is a much stranger challenge than you could possibly imagine.
So let's start with a question that sounds simple, but is actually, well, it's massive. Could we, in theory, build a computer that perfectly simulates our universe? Not an approximation. I mean an exact one-to-one copy that does exactly what nature does.
And here's our detective, Richard Feynman, laying out the case back in 1981. Now, this wasn't just some idle thought experiment. He was actually setting up a brilliant logical trap to test the very limits of our computers and, it turns out, physics itself. Okay, so to keep things fair, Feynman laid down one crucial rule. If you want to simulate a space that's twice as big, your computer should only need to be about twice as big. It can't suddenly need to be a billion times bigger. He was looking for an efficient, scalable solution, not some computational monster that would literally collapse under its own weight.
So, what's the big problem? Well, even for a simple classical system of particles, to simulate it, you have to keep track of the probability of every single possible arrangement. Where's particle 1? Where's particle 2? And 3? All the way up to the last one, R.
And right here, this is the mathematical nightmare. If you have n possible spots for r different particles, the number of combinations you have to track is n to the power of r. That number doesn't just get big, it explodes. Even a small increase in the size of your system makes the computer you need exponentially bigger. And just like that, we've broken Feynman's rule.
And here's the real kicker. You might think, okay, that's classical physics, but what about quantum mechanics? Well, in quantum physics, you have to calculate this thing called an amplitude function. And guess what? It also depends on the position of every single particle. We are right back where we started, facing the exact same too many variables problem. A direct simulation seems totally impossible.
But Feynman, being Feynman, was way too clever for that. He thought, okay, what if we're thinking about this all wrong? Instead of calculating all the probabilities, what if the computer could just behave like nature? What if it could just gamble?
And this led him to imagine a probabilistic computer. This is a brilliant idea. The machine doesn't try to compute that there's a 50% chance of something happening. Instead, it just has a little internal coin flipper and produces that outcome 50% of the time. It doesn't calculate the odds, it lives them. It's a really elegant way to sidestep that whole n to the r explosion.
This feels like a breakthrough, right? It seems like the perfect solution. Our universe is probabilistic, so let's build a probabilistic computer to match it. So this is the big question. Can this clever machine finally crack the code and simulate quantum physics, all while playing by Feynman's rule? And the answer, which is just stunning, is no. Not at all. This beautiful, elegant workaround completely shatters the moment it comes up against the deep weirdness of quantum reality. The classical dice-rolling computer just isn't enough.
So why? Why does it fail so spectacularly? Well, it all comes down to a concept so bizarre it honestly sounds like a typo. Let's call it the negative probability glitch. And it's the hidden catch that breaks everything.
And hey, if this part feels a little weird, don't worry, you're in good company. Feynman himself said this stuff made him nervous. He knew he was wading into territory where all of our everyday intuition just completely falls apart.
Okay, so take a look at this table. In quantum mechanics, to figure out the final odds of something happening, you first have to work with these intermediate numbers, these f values. And do you see it? See that second row? One of the values is negative. That's the glitch. It's a probability that is less than 0. How is that even possible?
Right, so here's why this is such a deal breaker. When you add up all these weird f values to get the final answer you can actually measure, the result is always a normal, positive probability. The math works out perfectly every time. But, and this is the whole point, a classical probabilistic computer can't start with a negative probability. It's just impossible. It's like trying to build a machine that has a negative 10% chance of landing on heads. It makes no physical sense. Now, you might be thinking, okay, this is just some weird math trick, right? Some clever accounting on paper. But it's not. There is a real-world experiment that proves this strangeness is not just in the equations, it is hardwired into reality itself. So, here's the setup. You have an atom that spits out two photons that are quantum mechanically linked, kind of like twins. They fly off in opposite directions. You're at one detector, I'm at the other.
We can each set our detectors to any angle we want to measure a property called polarization. After a bunch of measurements, we call each other up and see how often our results matched.
Now, there are two ways to think about this. The classical way assumes each photon left the atom with some kind of hidden instruction booklet, telling it exactly how to behave at any angle we might choose. Our experiment just reveals what was already there. But quantum mechanics says, nope. It says the outcome is genuinely random, undecided right up until the exact moment we measure it. Our experiment actually creates the result.
And this is where the rubber hits the road. If we set our detectors 30 degrees apart, classical logic, with all its hidden instruction books, predicts that at best, our results can only match 2/3 of the time, about 67%. But quantum theory, with its weird negative probabilities, predicts 3/4, 75%. And when you actually go into a lab and do the experiment, you get 75% every single time.
And I want to be really clear about this. That 75% result isn't just a little off. It is mathematically impossible for any system that works on classical, local rules. No matter how you try to program your probabilistic computer, no matter how clever your random dice rolls are, you can never reproduce what nature actually does. The workaround has failed. Reality has spoken.
So, where does that leave us? If no classical computer, not even a super clever probabilistic one, can possibly simulate quantum reality, what's the answer? Well, Feynman's chain of logic leads us to this incredible, breathtaking conclusion. We've been trying to build the wrong kind of computer all along.
And here's Feynman, just laying it on the line in his classic no-nonsense style. Nature isn't classical. So if you want to simulate nature, you'd better build a computer that plays by nature's rules, quantum mechanical rules.
And this is it. This is the logical birth of the idea of a quantum computer. It's a machine built out of quantum bits, or qubits, that obey the laws of quantum mechanics. It doesn't have a problem with things like negative probability, because that's its native language. It doesn't imitate the universe. It is a tiny, controllable piece of the universe.
And that, right there, is the beautiful, almost poetic conclusion to Feynman's entire puzzle. His quest to figure out how to simulate nature led him to realize that the only way to perfectly simulate a quantum universe is with a quantum universe. The best tool for the job is the job itself.
You see, this whole journey, this whole line of reasoning, it was never just about building a faster computer. It was a deep, fundamental investigation into the very fabric of reality. And it leaves us with this incredible, tantalizing thought. Now that we know what kind of machine we need to build, what kind of tool we need to use, what new, deeper mysteries about our universe are we finally ready to ask?